Good morning, guys. I am Tushar Chaoudhary, EPS third year student. My topic for CWS presentation is radiation sensor. So let's continue with radiation sensor. Introduction to radiation sensors. The radiation sensor is a device that detects and measures the presence and intensity of radiation in its surrounding. Radiation is a form of energy that exists all around us, coming from sources such as the sun, the earth, even our own bodies. These sensors play a critical role in protecting human health and environment from harmful effects of radiations. Radiation sensors work by using a variety of techniques to detect and measure the energy of radiation that passes through them. Some sensors use material that emit light when they interact with radiations, while others use the materials that generate the electric signal. Okay, so the type of radiation being detected and sensitivity required for particular application will be determined the type of sensor that is used. Radiation. So what is radiation? The radiation is energy. It can come from unstable atoms that undergo radioactive decay, or it can be produced by machines. Radiation travel from its source in the form of energy waves or energized particles or photons can be said. There are different forms of radiations. They have different properties and effects. There are two kinds of radiations: non-ionizing radiation, whose examples are radio waves, visible light, and microwaves. Non-ionizing radiations has enough energy to move an atom from a molecule or cause them to vibrate, but not enough to remove an electron from atoms. Example of this kind of radiations are as shown here. Okay, the radio waves, visible light, microwaves. And on the other hand, ionizing radiations has so much energy it can knock the electrons out of atoms. That process is known as ionization. Ionizing radiations can affect the atom in living things, so it poses a health risk by damaging tissue and DNA in our genes as well. Ionizing radiation come from X-ray machines, cosmic particle from outer space, and radioactive elements. Radioactive elements emit ionizing radiations as their atom undergo radioactive decay. Here we can see the electromagnetic spectrum where the energy increases. As the energy increases, there's the high frequency, high energy, the ionizing nature of the radiation is more. It can knock the electrons, it is more energized. Okay. So the classification of the radiation can be done as this: ionizing, non-ionizing. Ionizing can be classified into electromagnetic radiations and particular radiations that are charged particles, neutrons and charged particles. And on the other side, non-ionizing radiation, that examples are electric beam, microwave, infrared, red rays, visible rays, ultraviolet rays. Okay. Principle of radiation detection: when the radiation passes through material, it can ionize or excite the atom in its material, as we talked before. We can then detect, which can be detected by the radiation sensor. When the ionizing radiation interacts with matter, it causes the ionization and excitation events that produces charged particles, free electrons and photons. Radiation sensors are designed to detect and measure the charged particle, free electrons and photons produced by ionizing radiation or non-ionizing radiation interaction with matters. In this slide, we will talk about the interaction of ionizing radiation with matter. There are ionizing radiations: alpha, beta, gamma, neutron. So here the material is this. So alpha particles causes the beam strung long, and the charged particles interact strongly and ionize directly. These are the charged particles, and this is the neutral particle and neutron. And the charged particles interact strongly and ionize directly, and that the neutral particles interact less and ionize indirectly and penetrate farther. And so let's talk about the what is meant by the ionize directly and ionize indirectly. Okay, so direct ionization occur when ionizing radiation such as high energy photon charged particles, alpha, beta, gamma, directly collide with atom or molecule in a material and transfer enough energy to ionize them. This process can result in the formation of both positive ions and negative ions in the material. As you can see, there is the collision direct like this, the gamma interaction shown, beta interaction shown, and where in the indirect ionization in the case of neutron occur when indirect ionization occur when ionizing radiation interact with atom or molecule in the material, causing the atom or molecule to become excited. Okay, These excited atoms or molecules can then collide with neighboring atom or molecules and transfer their energy, leading to ionization. In indirect ionization, the energy is transferred indirectly from the third person, and indirect directly by the collision. And in the second thing, you can see that the neutron can pass through all except water and plasma. Like a neutron can pass from paper, thin aluminum plate, lead plate, and these have some limitations, and this is because of the nature of the particles. Types of radiation detectors: gas field detectors, scintillation detectors, and solid state detectors. So let's talk about gas field detectors. The radiation that passes through the air or specific gas filled in this. Ionization of that molecules in the air occurs when high voltage is placed between the two areas of the gas filled space. The positive ions will be attracted to the negative side of the detector, that is the cathode, and the free electrons will travel to the positive side, the anode. These charges are collected by anode and cathode, which then form a very small current in the wires going to the detectors by placing a very sensitive current measuring device. This is the current measuring device. The By placing a very sensitive current measuring device between the wires from the cathode and anode, a small current is measured and displayed as a signal that helps to relate the current and radiation. That shows the intensity of the radiation or the strength of the radiation. The two most common gas field detectors are ion chamber or Geiger-Müller tubes or GM detectors. Scintillation detectors. The basic principle behind this instrument is the use of special material which glows or scintillates when radiation interacts with it. That produces the light when radiation interacts with the material. Okay. The most common type of material is type of salt called sodium iodide. Sodium iodide produces light when it interacts with the radiation or radiation falls on it. And the photocathode produces the electrons when light strikes its surface. This is the sodium iodide crystal that produces the light, which then hits the photocathode that produces the electrons. The light produced from scintillation process is reflected through a clear window where it interacts with a device called photomultiplier tube. The first part of photomultiplier tube is made of another special material called photocathode. Okay, that photocathode produces electrons, then electrons goes to diodes. Okay, these electrons are then pulled towards a series of plates called diodes through an application of positive high voltage. When electrons from the photocathode hit the first part diode, several electrons are produced. For each initial electrons hitting its surface, this bunch of electrons is then pulled. These bunch of electrons is then pulled towards the next diode where more electron multiply occur. The sequence continues until the last diode is reached where when the electron pulse is now millions of times larger than it was at the beginning of the tube. The electron beams they collided. As you can see, the diodes also produce the electrons. Then after the certain number of reflections or collisions, there will be a significant calculatable pulse that can be measured of pulse of electron that can be measured by measuring device. Then we can say what was the strength or the range of the radiation. Solid state detectors. Solid state detectors provide a signal by collecting the charge liberated in the passage of particles through the semiconductor. The radiation passes through the semiconductor and the suitably implanted electrodes, typically strips, as you can see, these strips, apply an electric drift field in which the ionization charges are collected and induce a detectable signal. The silicon detectors are low energy radiations, can detect low energy radiations, and germanium detectors can detect high energy radiations. Okay. When the ionizing radiation interacts with the semiconductor material, it produces the electron hole pair where the electron and holes are free to move in material. The electron hole pair created by ionizing radiations are separated by the electric field in the semiconductor material, and the resulting current or charge is collected by the electrodes in the detector. The detection efficiency of the solid state detector depends on the thickness of the detector material, is proportional to the thickness of the detector material, and this means that a thinner detector being more efficient at detecting low radiation. It's not means like detection efficiency like thickness will cause the sensitivity problem, but this means to say that the thinner detectors being more efficient at detecting low energy radiations, and thicker detectors will be efficient at detecting high energy radiations. Okay, so here are the comparison among the different radiation sensors, the different detector types of sensors we talked in previous slides: gas field detector, scintillation, solid state. Then the type of radiation detected by them are gas field alpha, beta, gamma; by scintillation, gamma and X-ray; and the solid state wide range of radiation types means that these both, and beyond that also. The voltage source required in these all three are respectively these, like high, low in scintillation, low in solid state. Energy resolution is good in this, good in gas field, good in scintillation as well, and excellent in solid state detectors because of use of semiconductors, and we have quite knowledge of that. Size is large in gas field, they are quite large. Small scintillation detectors are there, and solid states are also small. Sensitivity is appreciable in solid state, that is high, and gas field also. Scintillation and moderate. Cost is they all are quite expensive, but gas is moderate. Radiation damage. This is the quite a challenging factor for us in the radiation detection. That they are also prone to radiation damage that cause. Okay, so the gas field are resistant to radiation damage, scintillation are susceptible, and solid states are resistant. The most damage was most affected by the radiation damage is scintillation detectors. The application of radiation sensors in nuclear power plants, in medical radiation therapy, environmental monitoring, managing the and maintaining the level of radioactive elements, and radio is, if there is any leakage from the earth or any site. Homeland security and defense, space exploration, archaeology and geology. In archaeology and geology, using the carbon dating or the radiation detection. Okay, the challenges and limitations in this radiation detection is like the background radiation. The first is background radiation. The radiation sensors can be affected by the background radiation, which is the ambient radiation present in environment. Actually, we also emit the radiation. This can make it difficult to accurately detect low level of radiations. Okay. Now, the second challenge is calibration. The radiation sensor requires a regular calibration to ensure accurate readings. Calibration can be challenging and time consuming, and may require specialized equipment and expertise. And the third challenge is radiation damage. Radiation damage can cause the damage to the sensors, which can affect its performance over time. This can be particularly problematic in high radiation environments, or the devices that is used to detect the high energy radiations. And the other challenge we can say is the sensitivity to temperature and humidity. Temperature and humidity can be also affect the measurement conditions of the radiation. Innovative idea. So the first innovative idea can be the autonomous radiation mapping drones. The drones equipped with radiation detectors can provide an aerial mapping of radiation levels in remote or hard to reach areas. This can be used for environmental monitoring or to identify potential radiation source in disaster zones. Okay, so where the human can reach, the drones can use radiation mapping to scan the area, and we can get the useful information. So other field that can use the radiation detection is the testing of materials, non-destructive testing. The radiation detectors can be used for non-destructive testing of materials such as metal or composites to detect any hidden crack or defects. Like the hidden crack or defects like will reflect certain amounts of, if where we give if the material is bombarded with radiation, and the certain cracks will respond to radiation differently, and they reflect back the different type of different radiation than the reflected by the material that is good. Okay, so that can be used to check any hidden crack. Okay, now this can be useful for quality control in manufacturing, for ensuring the safety of critical infrastructure. Okay, thank you. That was all from my side.